Welcome. Thank you for joining us. Today, we're going to discuss how ignoring the temperature variable can wreak havoc on your automated dispensing system. More and more, modern products are assembled with adhesives and sealers applied with advanced, highly automated dispensing systems. Automating this process eliminates variations caused by operator fatigue, distraction, etc. The repeatability that automation brings is a no-brainer. That being said, your outcome is determined by the physical properties of the fluid you're dispensing. And though these fluids are well engineered in the laboratory, even the most carefully crafted formulation and dispensing system can create unacceptable results due to uncontrolled variables in the application process. And one of the most critical is viscosity. In this presentation, we'll examine how variations in viscosity impact a fluid's performance in application, its intractable relationship with temperature, and how these factors affect outcomes in modern automated fluid dispensing systems. In this single example, which was made by a robot in a process like the one we just viewed, we see some of the more common sealer dispensing defects. Things like thin beads where insufficient material is applied to do the job. Heavy beads where too much material is applied, which can lead to slumping, where the bead flows out of its intended area. Then there's starting blobs and ending blobs, again, where too much material is applied for the application. And finally, there's tail off, where the viscous material is dragged away after the gun is shut off. All of these can occur in manual operations in spite of an operator's best efforts, but a robot can mindlessly repeat these problems part after part after part. These issues combine to produce results like this when our customers expect this. Believe it or not, all of these defects are related to temperature-based viscosity variations. Now, if you're not familiar with Sinclair Systems, we design and manufacture advanced point-of-use temperature and viscosity control systems for industrial fluid dispensing processes, and we've been doing it since 1990. And during that time, we've amassed more than 3,500 active installations all over the globe. Specializing in both recirculating and dead-end systems, we handle low viscosity materials like water and solvents that are less than 1 centipoise, all the way up to high viscosity materials like sealers and adhesives that are more than 1 million centipoise. To handle these applications, we have to be able to work at pressures from 5 psi, which is about 0.4 bar, to more than 6,000 psi, or more than 400 bar. So who cares? And the answer is lots of folks, as you can see here. This spans myriad industries like automotive, steel, plastics, composites, nanomaterials, food packaging, pharmaceuticals, and sporting goods, just to name a few. Each successful project with demanding customers such as these has increased our understanding of the ramifications of temperature and viscosity in a host of fluid dispensing applications. Yes, this is a shameless advertisement for Sinclair Systems, but it's also the reason we're qualified to be here today talking about this topic. So let's take a look at the fundamentals that created these issues in the first place. Let's start with the question, what is viscosity? A relatively simple explanation is the property of resistance to flow in a fluid or semi-fluid. Honey is a great example. Think of honey when you put it in the refrigerator. It gets thick, very thick, in fact almost solid, and sticky too. But take that same honey and run it through the microwave, and the change is dramatic. It thins out significantly and you can pour it, almost like water. This change in how it flows represents its change in viscosity, and in this case, as we're going to discuss a lot today, the cause is the change in temperature. Here's a viscosity versus temperature curve for a typical sealer or adhesive. While paint curves generally run in the range of 50 to 350 centipoise, sealers and adhesives run orders of magnitude higher, often falling into the range from 30,000 to more than 1 million centipoise. But what's really important about this curve is the steep portion of the curve from 18 to 26 C. That's about 67 to 78 degrees Fahrenheit. So it's right in the middle of the ambient range. Here, we can see that the viscosity falls from more than 80,000 centipoise to less than 40,000 centipoise. That's a 2-to-1 shift in viscosity over less than 8 degrees C. From this, it's easy to understand that small variations in temperature will produce large changes in viscosity, which will significantly impact the performance of the process. But there's another, often misunderstood parameter that becomes very important in modern advanced fluid formulations: Newtonian versus non-Newtonian behavior. This refers to whether the fluids change viscosity as a function of induced shear stress. For Newtonian fluids, changes in shear induced into the fluid have no effect on the viscosity. Water is a common example, but this feature is important in other fluids as well. Motor oils, for instance, where the lubrication efficiency must not degrade when it's placed in shear, like between two rubbing metal parts. Non-Newtonian fluids, on the other hand, show a significant change in viscosity when they're placed in shear. These are called thixotropic fluids. Initially, as the shear increases, the viscosity remains stable. This is called the first Newtonian range. As the shear continues to increase, the viscosity falls, often quite sharply, until it reaches the second Newtonian range, where the viscosity stabilizes again. Now, trying to control the viscosity between these two Newtonian ranges is very, very difficult. For high viscosity fluids, like sealers and adhesives, it's often better to design the dispensing system for laminar flow so as to work in the first Newtonian range, where, with coatings, it's often easier to add agitation and turbulence so as to work in the second Newtonian range. As we noted, while robotic systems can repeat the gun path, speed, angle and distance to the part, flow rate, and total volume of material on every dispense cycle, they can't compensate for the viscosity variations resulting from the ambient temperature swings that occur from morning to evening and season to season. And as we've seen here, temperature-based viscosity variations directly affect the shape of a fan pattern or bead being dispensed. Let's start by examining a standard spray system. In this anti-chip sealer application, we can see the impact of temperature on dispense and ultimately on performance. The most obvious change is in the width of the fan pattern, but perhaps even more important is the impact of viscosity on spray consistency. Above 35 degrees C, the coating is thin and uneven. You can see the substrate peeking through. Even if it adheres well, it can't do its job. In the 30 to 35 degrees C range, the coating is smooth from edge to edge. This is the optimal operating temperature for this particular process. Below 30 degrees C, when the viscosity is increasing, we see heavy edges beginning to appear, which are often associated with striping on the finished part. And as we moved into the 25 degrees C range and below, we see the combination of very uneven coating surrounded by heavy edges, which makes it very difficult to get a smooth, even coating on the finished part. And without a smooth, even coating, both performance and appearance will be compromised. Now, an operator must compensate for these changes by making adjustments to the pressure regulator and or through eye-hand coordination, adjusting overlap and respraying thin areas. At lower temperatures, the heavy edges produce too heavy a build in the overlap area, resulting in striping and sag issues. And when robotics are employed, eye-hand coordination isn't an option, and the problem can be repeated over and over again. And it's no different for fixed displacement dispensing of beads. In this typical hemflange application, the change in width of each bead as a function of temperature is obvious, with the width at 38 degrees C nearly double that at 16 degrees C. Perhaps not so obvious, though, is that Because each bead is comprised of the same volume of sealer, the change in width is offset by a change in height. The wider beads are also flatter. This is often referred to as spread or slump and can significantly compromise the function of the bead. Without the proper profile, obtaining optimal adhesion to both surfaces is next to impossible. Moreover, if the material moves out of the designated area, it can create not only functional issues, but aesthetic ones as well. So, what factors affect temperature anyway? It's the ones that we all know. There's the ambient temperature. There's the material storage temperature. There's the volume of the fluid in the source container because of its thermal mass. There's the flow rate that we have to move the material at. And if it's recirculating, it's the rate at which it recirculates and the path through which it recirculates. Does it go up into the truss level? Does it go down into the basement where it's cold? This determines the pressure settings, and that determines what pump type we need and how big that pump has to be. Because to move fluid, we have to impart energy into it. And when we impart energy, we generate shear and friction. It comes from the pumps, the filters, the regulators, the nozzles, the fittings, things like that. And it's important to remember that friction and shear equal heat. This is the reason that simply controlling ambient temperature is not an effective means of temperature control. Besides, it's also important to remember that often the fluid we're dispensing comes into our carefully controlled dispense booth from a totally uncontrolled area. The goal, then, is to stabilize and optimize the temperature and therefore the viscosity of the sealer or adhesive at the point of application, which for most systems is the nozzle orifice. With very few exceptions, no other material temperature in the system matters to the stability of the application process. So again, I want to thank you for taking the time to be here today. Though in this brief 15 minutes, we've only scratched the surface of what stable temperature and viscosity can bring to your dispensing operation, I hope that we've opened a new window through which you can evaluate your processes. So at this point, I think we have time for a couple of questions.